I guess it's my honor to introduce Noah Stevens Davidowitz. He is the newest member of the CAM field as of yesterday, and he is a relatively new member of the Cornell faculty as of September. His area is theoretical computer science, broadly speaking, but more narrowly, I guess, post-quantum or lattice-based cryptography, and that's what he's going to tell us about. He has a postdoc from NYU and has an interesting history of doing, has a PhD from NYU, supervised by Oded Regev. And he has an interesting set of postdocs with an amazing mix of Berkeley at the Simons Institute, at MIT, and Princeton, which I guess is a cool and varied set of postdocs with interesting experiences, which I think is a great start to life, kind of similar to I started with a lot of postdocs also, so like my start in life. I don't want to take away a lot of time from Noah, so I'm going to stop here. We are thrilled to have him as a Cornell faculty member and as a CAM field member. I guess for rules for interaction during the talk, especially if you have some noise in the background, like a crying kid or dog or whatever, please mute your mic. If you have any questions, Noah says you can aggressively interrupt him, or if you're too timid for that, you can raise your hand and I can try to interrupt him. Or he says he might be able to monitor the chat window and you can test his ability to do this and put a question in the chat window. These are all options. And with this, I should let Noah speak.
Great. So thanks, Ava, and thanks to the CAM field for inviting me and for having me as a member. It's an honor. Yeah, so as Ava said, please interrupt me aggressively. You know, like I've heard this talk before, so I'm going to get bored unless people say something interesting to me. So yes, so today I'm going to be talking to you about the foundations of lattice-based cryptography. And I guess I should probably say, you've all probably forgotten by now, but I think a decent fraction of you saw my job talk last spring, and this is more or less the same talk. So I apologize for that, but I bet you've forgotten, so it'll be okay. So we start out with a real world problem. So here's our real world problem. David wants to buy something on the internet. This comes up every once in a while, I imagine. And I think the way that we typically think about this happening, or like we typically think about this problem being solved, is there's sort of some magical wire that goes between David and Amazon. And David uses that magical wire to send his credit card information. You know, so like you can sort of make this into an extreme caricature, like there's some wire that comes out of David's computer and like runs all the way west across the Mississippi River, across the Rocky Mountains, and then maybe north a little bit, and stops in Seattle on some Amazon server. But of course, in reality, like we don't have these private wires between all pairs of computers. Instead, we use some complicated beast called the internet. And the internet is a sort of scary place full of shady characters. So that if David were to send his credit card information, this is actually, by the way, his real credit card number. If he were to send his credit card information across the internet, you know, some shady character like this guy over here would likely read it and, you know, buy some stuff with it. And David would be sad. So we don't do that. Instead, we have to somehow send this credit card number in an encrypted way so that Amazon can read it, but the shady character over here can't. And there are many ways to do this. I'm here to talk about lattice-based cryptography, so I'm going to describe to you how to do it with lattices. So first, I'll tell you what lattices are, and then I'll tell you how to solve our real-world problem using lattices. So a lattice is a beautiful geometric object. It's a discrete periodic set of vectors in n-dimensional space. So this is a lattice in 2 dimensions. If you can picture 500-dimensional space, then please do. But for the purpose of this talk, I'll keep n equal to 2. You should keep in mind that n really is going to infinity. It's specified by a basis B1 through Bn of linearly independent vectors. So this is a basis of this lattice. There's just 2 of them. They're named B1 and B2. And the lattice itself is the set of all integer linear combinations of the basis vectors. So I take an integer times B1 plus an integer times B2 plus an integer times B3, etc. For example, this is a lattice vector. It's a lattice vector because it has integer coordinates in my basis. It's 2b1 plus b2. This is also a lattice vector because it, again, has integer coordinates in this basis, minus b1 plus 2b2. You can check me, I'm not lying. Now, an interesting fact about lattices, which is maybe not immediately apparent, is that the basis of the lattice is not unique. So I showed you one basis for a lattice. It's really a rather nice basis, consists of short vectors that are roughly perpendicular to each other. But this is another basis. It's somehow not as nice. The vectors are much longer, but it's also a basis of the same lattice. And that's maybe not immediately obvious, but you can check it yourself by just seeing that my original two basis vectors, b1 and b2, can be written as integer linear combinations of my original basis vectors. And computationally, it's difficult if I give you a long basis of a lattice to find a short basis of the lattice. You can see like a short basis is somehow more useful, right? Like when I give you B1 and B2, if I just gave you those and nothing else, you'd have a pretty good idea of what the lattice looked like. But if I give you this sort of skew basis, these two very long vectors that point roughly in the same direction, it's really not clear what the lattice looks like. You'd have to do a little bit more work to figure it out. And of course, I'm describing all of this for you sort of misleadingly in 2 dimensions. In 2 dimensions, this is actually easy. But as dimensions get much higher, sort of long bases are like very uninformative. And in particular, it's computationally difficult to find a short basis given a long basis. So this is sort of the key computational problem that we're going to use to solve our real world application here. So let's come back to David and Amazon. So David wants to get his credit card number to Amazon. So here's what they'll do. Amazon is going to come up with some lattice together with a short basis. So there are like fancy ways to do this, but for the purposes of this sort of very high level talk, let's imagine that Amazon just samples 2 vectors that are short, or I guess n vectors that are short, uniformly at random in n dimensions, and takes them to be its basis for its lattice. And Amazon's going to keep this basis private. It will be its secret key, so it's not going to tell anyone. Now, doing this alone, of course, isn't very interesting. Amazon has some lattice. Nobody else has ever heard of it. I don't know how David would use that to communicate anything with it. So what Amazon also does is it gives David a bad basis for the same lattice. So you can see that this particular basis is so bad that it doesn't even fit in the little box I gave to it. But this is Amazon's public key. So it's literally public. It gives it to David, but not only David, to everyone. It publishes it on its website. This is more or less what happens in practice. And then David will encode his credit card number as a lattice point. So, I mean, we're all computer scientists and applied mathematicians, so like we know that there are many nice ways to encode different discrete sets into other discrete sets, but like in this particular case, like a credit card number is a list of integers. And actually, once you fix a basis for a lattice, then a lattice point is also a list of integers. It's the coordinates in that basis. So there's like a trivial encoding here. So David will encode his credit card number as a lattice point like that. But David's not going to send the lattice point to Amazon. If David were to send the lattice point to Amazon, then anyone who had access to the public key, like our shady character from a few slides ago, would be able to do a little linear algebra and figure out David's credit card number. So that would not be secure. What David does instead is he adds a little bit of noise to the message. So he takes a noisy point in space, not a lattice point, that's near his original lattice point, and that's what he sends to Amazon. And the sort of magic here, well, there are a few magical things. The first magical thing is that Amazon can decode David's message. So this is a good way to communicate something at the very least. And the way that Amazon can do this, there are fancy ways, but a simple way would be for Amazon to use linear algebra to write David's point in space as a linear combination of its basis vectors. Now, because David didn't choose a lattice point, because he added a little bit of noise, when Amazon does this, it won't get integer coordinates. It'll get some coordinates in its basis, but they won't be integers. But because David just added a little bit of noise, and because Amazon's basis is so nice and short, the coordinates will be close to integers. So then what Amazon can do, it can just round those numbers to the nearest integer. And if everything was done properly, if David didn't add too much noise and the basis was sufficiently short, then you can prove that Amazon will get David's original message. So Amazon will get David's credit card number. So this works. More than that, this is a public key encryption scheme in the sense that anyone who has access to the public key can do what David did, right? They can encode something as a lattice point, add a little bit of noise to it, send it to Amazon. So this is a public key scheme. You don't need the secret key in order to send a message. And none of this would be interesting if it weren't secure, but we also think that this is secure. In particular, an adversary who only has the public key shouldn't be able to decode David's message. And as far as we know, it would take 2 to the constant times n time to decode this message. Not for this specific scheme, like please don't go home and implement this. A reasonable variant of this scheme actually does work. And it should take exponential time in this key parameter, the dimension n, in order to decode this message. So easy for Amazon to decode, hard for our shady character, the adversary, to decode. So this is a public key encryption scheme. And public key encryption is absolutely magical. I think if I tell you that this is the problem, that we want anyone to be able to send a message, but only Amazon to be able to read it, coming up with a scheme that actually does this is really quite difficult. Then I showed you this scheme, which I hope seems fairly simple to you and sort of hides how magical actually this application is. But because this is so magical, we do know other ways to do it. This is not the only game in town, but the number of ways that we know to do it is really quite few. There are 3 main ways. You might have heard of the RSA-based encryption scheme. This was invented by Ravesh, Shamir, and Edelman in 1977, excuse me, back in the 70s. And I'm not going to tell you how this scheme works, but the rough idea is it's based on factoring in the sense that the public key is the product of 2 primes P and Q, and the secret key is those 2 primes P and Q. So without telling you what the scheme is, hopefully you can see that if it's easy to compute factors of a number, then it's easy to break this scheme. Then you can get the secret key given the public key, and the scheme will be insecure. So RSA is only secure if factoring is hard. Actually, what we use in practice are these discrete log-based schemes, which I'm not going to describe for you. They're due to Diffie and Hellman. They actually slightly predate RSA. But actually, that's what's used on the internet. And these 2 schemes together, mostly the discrete log stuff, are tremendously important. Nearly all secure communication uses one of these 2 schemes. In particular, far more than half of all internet traffic uses these schemes via the TLS protocol, right? So if you have a little lock on your browser, that means that one of the, your browser has done some number theory. Probably right now, all of our computers are doing a little bit of number theory in the background. And the reason that these 2 schemes are used, as best I can tell, is historical. It's because they were discovered in the 70s. Whereas lattice-based crypto was discovered 20 years later. The first scheme, kind of the scheme that I showed you, was discovered by Aitai and Dwork in 97. And my advisor, Oded Regev, I mean, he just won the Gödel Prize for sort of providing the modern version of lattice-based crypto. But this is really not used in practice right now. And that would probably stay that way. We would continue to just sort of live our lives using RSA and Diffie-Hellman, except for one sort of really unfortunate fact, which is that both RSA and Diffie-Hellman, both factoring and the discrete logarithm, are known to be easy for quantum computers. So if someone builds a reasonably large quantum computer, then they can factor efficiently, they can solve discrete log efficiently, and they can break all of our crypto schemes that we use currently. This was discovered by Peter Shor all the way back in 1994. But you might have heard that there have been a lot of recent advances in building quantum computers. I'm not an expert on this topic. I have no idea when or if quantum computers will be built, but I do know that people who think about this seriously are very concerned. For example, the National Security Agency, so the US spy agency, released a very cryptic message in 2015, just sort of saying, we think it might be a good idea to switch to schemes that aren't known to be broken by quantum computers. What they specifically said is we will initiate a transition to quantum resistant algorithms in the not too distant future. What they really meant by this, so the NSA is in charge of, well, they do many things, but one of the things that they do is they decide what encryption scheme the US government uses. And they meant the US government no longer wants to use stuff that can be broken by a quantum computer, no longer wants to use factoring and discrete log-based stuff, because they're concerned that this stuff will be broken. that quantum computer will be built in the not too distant future. Lattice-based constructions, in contrast, are not known to be broken by a quantum computer. So they're the leading candidates for what's called post-quantum cryptography, which is a very fancy name for saying public key cryptography that's not known to be broken by a quantum computer. In particular, the quantum attacks that are known by Peter Shor and others don't seem to apply to lattice-based crypto. And I often get questions saying, like, what's so special about lattice-based crypto? Like, why isn't lattice-based crypto broken by quantum computers? And so I'll kind of preemptively respond to this and just say that actually that question's backwards. The real question is, why did we get so unlucky that quantum computers happen to break factoring and discrete logarithm? There are very few problems for which we know a gigantic quantum speedup. I know three. The third is simulating quantum systems, and the other two are factoring a discrete logarithm, which nobody really wants to do in practice. Their only real application is breaking crypto. So we somehow got really unlucky that we happened to base the internet on one of the few computational problems that seems to be hard for a classical computer, but not for a quantum computer. We plan to switch. And even if you don't care about post-quantum crypto, even if you're a theorist like me, it turns out lattice-based crypto is kind of really magical. There's tons of magical things that you can do with lattice-based crypto. I mean, look, I think that public key encryption is magical, but there are even more amazing things like fully homomorphic encryption, which you might have heard of, or obfuscation, which is sort of a crypto complete problem. If anything a cryptographer would ever want to do, you can do if you can obfuscate. These are all known to be constructible by lattices, and essentially only using lattice-based crypto. So sort of don't take my word for it. Let me just sort of appeal to a third-party authority. The Simons Institute, where I was a postdoc last semester, as part of a program that they had on lattices, gave the following quote. They said that the role of lattices in cryptography has been revolutionary and dramatic, as a new way to realize powerful and game-changing notions, such as fully homomorphic encryption. So they've been a total game changer. This is something I probably shouldn't admit, but I guess now that I have a job, maybe I can. I once counted all of the submissions to a crypto conference that mentioned lattices or LWE or something related to lattices in the title, and it was a full third of the submissions. So this is a really big deal. This stuff has sort of conquered cryptography. But I don't work in that area. So I don't build things, or I barely ever build things based on lattice-based crypto. Instead, so I don't live in this nice, beautiful city that I'm showing you here. Instead, I sort of live down in the dirt. So what I like to work on is the foundations of lattice-based cryptography, and particularly the computational foundations. So remember that the sort of caricature of a scheme that I showed you, the public key was a bad basis for a lattice, and the secret key was some short vectors in a lattice. So the computational problem of finding the secret key given the public key, which is more or less the computational problem that you need to solve if you want to break the scheme, is the problem of finding a short vector in a lattice, which is called SVP for the short vector problem. And so this is a computational problem that I spend a lot of time thinking about, and it's extremely well studied. The fastest known algorithms for this problem, as I kind of already told you, run in time that's exponential in this key parameter n, the dimension of the lattice, 2 to the sum constant times n. That was a breakthrough result of Itai Kumar and Shiva Kumar in 2001. And depending on how fast or slow I talk, I may or may not show you that algorithm. And there's since been a ton of work, some of which I was a part of, working on getting this constant c as optimal as possible. So that's sort of the algorithmic side. There's also sort of complexity theoretic study of this problem. In particular, if you phrase this problem correctly, then it's actually an NP-hard problem. The problem of finding the shortest non-zero vector in a lattice is known to be NP-hard. And that was a massive breakthrough result, again by Itai in 1998, later improved by Machancho the same year. It was open for about 20 years before that. And the kind of short vector, so like I don't want to be misleading, so I want to say something slightly technical, which is that the kind of short vector that we know it's NP hard to find is not the same as the kind of short vector that we need to break lattice-based crypto. So it's not exactly saying that lattice-based crypto is NP hard to break, but it's something close to that. And the moral of this story is that we think it's very hard to find, we think it's very hard to break lattice-based crypto. So unless P equals NP, we know that you can't find shortest lattice vectors in polynomial time. That's proven under the mild assumption that P doesn't equal NP, which is an important assumption for me because I'd have no job otherwise. And we think that this provides really strong evidence that you can't break lattice crypto in polynomial time. And I should say, like, this type of evidence does not exist for other cryptographic schemes. For example, for RSA, there's no sort of closely related NP hard problem. Like factoring is not NP hard, for example. So you have these really powerful and useful computational hardness foundations on which this beautiful city that we've built of lattice-based crypto rests. But as lattice-based crypto has found more and more applications, you know, it's gotten really crowded in our beautiful city. So more and more people have started using it for more and more things. And they're really sort of putting strain on this computational hardness foundation. So I already sort of told you one example. I'll be a little more concrete now. We're planning to move like TLS, like the internet, over from lattice-based, from factoring and discrete log-based cryptography to lattice-based cryptography sort of as quickly as possible. And this is a formal procedure that's being done by NIST, the National Institute for Standards and Technology. They're like a US government standardization body. And they're trying to decide exactly how we're gonna use lattice-based cryptography to sort of run the internet. Good, so I see a really nice question in chat. The question is, what about approximating short vectors? Is that hard also? If not, would it help break encryption? And that's exactly the right question. So we know that finding the exact shortest vector is NP hard. Finding an approximate shortest vector is almost certainly not NP hard. And to break lattice-based crypto, all you need to do is find an approximate shortest vector. So that's the sort of, what's the game called? I'm playing hide the ball a little bit. I'm moving the goalposts around. For the purposes of this talk, I don't want you to worry about the distinction tremendously, but you're right, that distinction is sort of really important, and it's what I spend a lot of my time thinking about. So the standardization process is happening. It's not just happening in the public sector, it's also happening in the private sector. So if you want to run lattice-based crypto right now on your computer, you can download Google's Canary browser, which is the beta version of Chrome. And then whenever you interact with, I think, any Google site, you'll use lattice-based crypto instead of Diffie-Hellman. Sort of practical people aren't just interested in lattices for their post-quantum properties. They're also interested in this magic, like fully homomorphic encryption. In fact, by now, sort of every major tech company has their own fully homomorphic encryption library. I'm showing here Microsoft's, which is called Seal. I'm mostly showing theirs because I thought their graphic was kind of pretty. This is great. I mean, this is wonderful for me. I love that people are using this stuff. The scary thing is that, like I said, look, there's probably no polynomial time algorithm to break this, polynomial and n. But of course, when you build these things in practice, n is a number. It's not a parameter that goes to infinity. In practice, n is about 500. That's kind of what you need for efficiency. So you work in 500 dimensions, which, you know, sounds pretty fancy. But it would mean that if there's a 2 to the square root n time algorithm for SVP, that would be a total disaster, right? It would go from, like, right now, we think these things can't be broken in time. Like, okay, it's debatable whether or not if you had a computer that covered the entire surface of the Earth, whether it would complete the computation before or after the sun engulfed the Earth. Unclear. So that's what we think the security is. But if it turns out that you can run this in 2 to the square root n time, then my laptop breaks it in a second, right? So this is a large gap. Even a 2 to the n over 20 time algorithm would be a complete disaster, would make this stuff totally insecure. And in order to fix that, you'd have to make n be so large that it would be horribly inefficient and nobody would ever use it. So somehow the fact that we are quite sure that there's no polynomial time algorithm is not enough information for these applications. It's good, but it's not what we need. And if you're a theorist like me and like practice kind of scares you, it turns out that even for theory, this no polynomial time algorithm argument isn't strong enough. Like here's a list of sort of magical things that we know how to build from lattices, like obfuscation, which Raphael and Romain recently had a really major breakthrough in with others. And all of these sort of just beautiful theoretical objects are only known to be constructible under the assumption that lattice-based crypto is really hard, not just hard for a polynomial time adversary to break, but even hard for super polynomial time adversaries to break. In particular, all of these things would be broken, or their security proofs would be vacuous if we found a 2 to the square root n time algorithm for this problem. So again, don't take my word for it. Let me just summarize by saying what the Simons Institute says about this. They say that before lattice-based cryptography goes live, we need major advances in understanding the lattice problems that underlie the security of these crypto systems. I've underlined a sort of very important word here, which is the word before, which I think of as sort of the whole impetus behind what I'm doing. So before this stuff goes live, before we base the internet on this, we should understand this as soon as possible. Let me just finish the quote. The need to thoroughly understand lattice problems is greater now than ever, given the possibility that secure communication on the internet and secure collaboration on the cloud soon might be powered by lattices. So we want to figure this stuff out, and there's a clock on it. It's unclear when the clock sort of, like what the timer actually is. Like, is it going to be 5 years? Is it going to be fewer than that? Not clear, but we want to figure this out before we run the internet on it. I view this as kind of a personal mission. Okay, so I've not told you anything about what I do, or I've barely told you what I do. Let me now tell you sort of what I like to think about in this story. And there are kind of two sides of it. There's the Jekyll side. So Jekyll is the good guy, and there's the Mr. Hyde side. Mr. Hyde's the bad guy. So let's talk about the bad guy first. It's kind of more fun. So the bad guy comes up with algorithms for lattice problems. So I've come up with algorithms that find short vectors in lattices. And you can think of these as essentially attacks on lattice-based cryptography, hiding many, many details. So let me give you a very brief history of the running time of algorithms for SVP. So I told you that these things run in time that's exponential in the dimension. And we've been improving the constant in the exponent over the years. In particular, sort of before, back in 2010, before I was in academia, back when I was a poker player of all things, the fastest algorithm was this beautiful algorithm due to Machancho and Vulgaris, which ran in 4 to the n time. Really beautiful algorithm. And in 2015, we discovered a 2 to the n time algorithm for the same problem. That was with Devesh Agarwal, Daniel Dedouche, and Oded Regev. And in subsequent works, we simplified the algorithm in various ways. If I have time, I'll show you some of this algorithm. And just recently, it's online now, but it still hasn't been peer reviewed. We discovered a 2 to the n over 2 time algorithm for essentially the same problem. There's a little asterisk here. The asterisk means that I move the goalpost, I solve a slightly different problem, but it's good enough for applications. So anyway, the way that you can think of this, very, very roughly, is that every 5 years, Mr. Hyde comes along and says you have to double your key size, right? So every 5 years, he says, if you want the same level of security, then n has to be twice as large, which is a convenient fact that this pattern seems to hold. It's kind of been the Moore's law of lattice-based crypto. So every 5 years, double your key size. We hope that this pattern ends eventually. And we have very strong reasons to think that it does. So that's sort of the bad stuff. The good stuff is proving lower bound. So I tried to prove hardness results for this problem to convince ourselves that really this stuff is secure. And I sort of already told you one lower bound, which was proven all the way back in 1998 by Itai. He showed that SVP is NP hard, which is a polynomial time lower bound. As long as P doesn't equal NP, it means there's no polynomial time algorithm for this problem. But as I pointed out before, sort of we want something stronger than that. And luckily we have something stronger than that. This is what I've been kind of obsessed with over the past 3-4 years. Has been showing that there's no 2 to the epsilon n time algorithm for this problem. So we know that the optimal running time for this problem is exponential. This is under some complexity theoretic conjecture. You have to make some assumptions. But for the purposes of this talk, let's just pretend I proved there's no 2 to the epsilon n time algorithm. Here, epsilon is some pathetically small constant. We don't even bother to calculate it. So it's not like we have tight upper and lower bounds. And as I mentioned a couple slides ago, if epsilon turns out to be even less than like 1/20, then lattice-based crypto will be insecure and it would be a disaster. But what I view this is as like really strong evidence that we're not missing something huge. You know, we're not living in the world of 2 to the n and 2 to the n over 2 time algorithms when it turns out there was a 2 to the square root n time algorithm that we were missing this whole time. So I view this as really strong evidence that like we kind of understand this problem. Okay, so now is a really excellent time for questions in case you've been holding on to them. If not, I'll go into a little bit more detail.
You're willing to give us a rough estimate of how tiny that epsilon is?
Oh, I mean, so the real answer is that the complexity theoretic assumption we make has an unspecified constant in it, and it depends on that unspecified constant. I am working right now with Rajendra Kumar and Devesh Agarwal to try to come up with some sort of like, it's weird, it's a heuristic for a lower bound. We want to come up with a heuristic idea for what we think that epsilon should be. And we think we can get it to be larger than 1/100, for example. So like, it's not galactic, but yeah, we're making stronger and stronger assumptions and seeing how large we can get it is kind of the game. Yeah.
Is there this, I mean, there's this trade-offs between worst case complexity and average case complexity? What's the?
Yeah, so this is an excellent question. So everything I've been telling you has been misleadingly about worst case complexity. We do know for lattice-based crypto, a worst case to average case reduction. So we do know that breaking lattice-based crypto is as hard as a worst case problem. And that problem is finding a short vector in a lattice. But annoyingly, the definition of short changes. So everything that I'm proving a lower bound on is a worst case problem that doesn't directly apply to lattice-based crypto. But going into slightly more detail than I probably should, it turns out that the only way we know how to solve the approximate problem is via a non-trivial reduction to the exact problem in lower dimensions. So I actually view these as lower bounds on a technique for solving the approximate problem, the technique that goes through the exact problem. But I think I probably should avoid saying too much more about that in this mixed audience.
Thank you.
More questions? These are wonderful. Okay, I think I'll move on. So let me show you an algorithm, a really beautiful algorithm. It's not due to me, so I can say that. It's Itai Kumar and Shiva Kumar's sieving idea. This is more actually sort of an algorithmic framework. So let's like remember the problem that we're solving. So there's some underlying lattice, right? But we don't like get to see that lattice, right? So somehow the pictures I show you are kind of misleading because you just see all the lattice points. But of course, what you're given is just a basis for a lattice. You're just given a few lattice vectors. In 2 dimensions, you're just given 2 lattice vectors. So here's, I don't think this is actually a basis, but let's pretend. Here's a basis for our lattice. And the way sieving algorithms work, step 1 is for them to take these few lattice vectors that we get as input and sort of multiply them, get many lattice vectors that are all roughly the same length. And you can think about like, there are very fancy, clever ways to do this, which I might say a little bit more about. But the rough idea is you can take random small linear combinations of your original basis vectors, small integer linear combinations of your basis vectors. This will give you more lattice vectors, and they'll all have roughly the same length. Like between friends, they're all the same length. So now we have many, many lattice vectors that all live in some ball. They're not short lattice vectors, but they live in some finite ball. And you can prove just sort of basically geometrically, that if you have many vectors that all live in the same ball, then you have to have a pair of them that are necessarily going to be close together, right? Space gets crowded eventually. If in particular, you need exponentially many vectors to make this work. But eventually we'll find some pair, like this pair I've highlighted over here, that will be close together. So this is a pair of close lattice vectors that we know. And of course, if we take their difference, one nice thing about lattices is that they're closed under differences. So if I take their difference, I get another lattice vector. And since they were close together, I get a shorter lattice vector. right? So this lattice vector that I found here, this purple vector, it's a lattice vector, and it's much shorter than my other vectors. It's not a shortest vector, but it's a lot of progress. And if we have enough vectors, enough red vectors, then we can keep going. We can find another pair and take the difference of that pair, find another purple vector, and another pair, take the difference of that pair, find another purple vector, and so on. So I made this slide back in like, I don't know, 2017 or something. And I've been milking it ever since. It's by far the best slide I've ever made. So you keep going many, many times, and eventually you get many, many purple vectors. Sometimes something kind of funny happens, which like, I kind of want to sweep under the rug, but it's a really big issue, which is like, now I'm looking at this new pair of red vectors up here, and notice that when I take their difference, I actually get a purple vector that I already had before. This is called a collision, and it's kind of a huge bummer. So now I got the same vector twice. But okay, let's forget about the collisions for a second. Now I got a bunch of purple vectors, tons of them, and they're all pretty short. So space is going to get a little crowded. And what's going to happen is I'm going to find pairs of them that happen to be close together. And then I can take differences of those, and I'll get a green vector. And in reality, I could milk this slide for an hour, but in reality, we run this many, many times. Here, I'm sort of, to save us from going insane, I've stopped things here. I've actually found a shortest vector. But the way this algorithm works in general, you start out with exponentially many not too long vectors, maybe sampled randomly in some clever way. And we just keep taking differences of closer and closer pairs until we find a shortest non-zero vector. This is a beautiful algorithm, I think. It's a really, really natural technique. If you want to find short lattice vectors, what do? You find a bunch of long lattice vectors, and you find pairs of them that are close together and take their differences. Really nice, really simple. In particular, what's beautiful about it is that there's a clear sense in which you make progress at every step, right? At every step, I'll just sort of define my threshold of what counts as short to be a little shorter. In that way, I sort of know that I'm getting shorter and shorter vectors at every time. And of course, the best thing about this algorithm is that it can be made to work. But I say it can be made to work because it takes a lot of effort to make it work. In particular, this is a very hard algorithm to analyze. It's somehow too simple to analyze. And the huge difficulty is that even if I start out with some beautiful distribution, like this distribution here on the left, this is the discrete Gaussian distribution. It was the topic of my thesis, but I'll try not to say too much about it in this talk. But I can start out knowing exactly where my vectors came from, exactly how they're distributed, but then I do this kind of overly simple, kind of ugly operation where I look at pairs of vectors and I take their differences if they're close together. And that operation of looking at pairs that are close and taking their differences is very difficult to analyze. So after I do this, like sort of one or two times, well, I'll get sort of an uglier distribution that I already kind of don't know how to analyze. And as I keep going, I'll get uglier and uglier distributions. So this is just kind of my depiction of an ugly distribution that's hard to understand. So while it's trivial to prove that my vectors get shorter and shorter at every step, what's actually hard to prove is that I don't see too many collisions. So the only thing we don't know how to prove is that somehow the distribution of vectors that I get isn't tremendously concentrated on just one vector, say, or on a small set of vectors. And because we don't know how to prove that, or because our ability to prove that is pretty weak, we get pretty bad running times for these things. So the fastest running time that actually uses this idea purely is 2 to the 2.5n. And that's entirely because we don't know how to bound the probability of collision. So we have to start out with a ton of vectors just to get anything going. What we did is we decided with Devesh, Daniel, and Oded to sort of really stare at this distribution, the discrete Gaussian. I already mentioned it's a topic of my thesis. I think a lot about this thing. So what the discrete Gaussian is, in a small amount of detail, it's you take the lattice and you assign to each lattice point probability proportional to this Gaussian mass, e to the minus norm squared over s squared. And the only thing you really need to know about it is that it comes with this parameter s. And this parameter s you could think of as like a standard deviation or a width. So in particular, as s gets smaller, the distribution gets narrower, which means that my vectors get concentrated, my distribution gets concentrated on shorter and shorter lattice vectors, which is kind of what we want, right? So what's known and what's already was used in the sieving algorithms is if you want to sample from this distribution for very large parameters S, we can do that. In fact, it's pretty easy. In other words, if you want long lattice vectors that are distributed like a discrete Gaussian, that's not hard, which maybe isn't so surprising because it's not hard to find long lattice vectors. What we decided to do, well, rewriting history a little bit, is instead of trying to start out with these nice Gaussian vectors and then just making them shorter but losing the Gaussianness, what if we can preserve this nice distribution at every step? So the idea is to start out with discrete Gaussian vectors with some large parameter S, and then to keep dropping the parameter, somehow convert them into vectors that are Gaussian again with a smaller parameter. And if we could do that, then we would immediately solve SVP, because then we would know the distribution of the vectors exactly, wouldn't have to worry about this like weird collision thing or anything like that. So this is the idea. To make it work, well, to get intuition for this weird discrete Gaussian distribution, your intuition should come from the continuous Gaussian. So I want some way to pair two Gaussian vectors together in a way that will give me a smaller Gaussian vector, a Gaussian vector with smaller standard deviation. And I don't know how natural this is, but like, okay, one way to do it is to take the average, right? If I take the average of two Gaussian vectors that both have parameter S, I'll get a new Gaussian vector that has parameter S over square root 2. Right, this is just the fact that like variances add. So you can ask the same question about the discrete Gaussian. If I take two lattice vectors, sample from the discrete Gaussian, and I take their average, is the result a discrete Gaussian distribution on the same lattice with parameter lowered by a factor square root 2? And the answer is no, absolutely not. If I take the average of two lattice vectors, this is a really bad idea because in general, the average of two lattice vectors will not be a lattice vector. So like, I mean, I'm telling you about this because it works out, but right now it should seem really silly, right? The whole point of the sieving algorithm was I use this operation of taking differences because lattices are closed under taking differences. And now for some reason, I'm telling you about taking averages, which seems really stupid because lattices aren't closed under taking averages. But it turns out that if you force this through, it really works. So in particular, if you stop and think, well, what do I need to be true about pairs of lattice vectors for their average to be in the lattice? And I'm kind of going to go through this quickly because I think I'm running a little low on time. But well, if you have two lattice vectors with coordinates aij, and you take their average, well, the coordinates of the average are the averages of the coordinates. So this resulting average, this will be a lattice vector if and only if all of these coordinates are integers. And that will happen if and only if the coordinates of the original vectors have the same parities. Yeah. So if my first vector had first coordinate odd, and my second vector also had first coordinate odd, then when I take their average, the result will have integer coordinate. The fancy algebraic way to say this is that y1 and y2 should lie in the same coset modulo twice the lattice. And what we proved is that this is the only obstruction. So if you condition on two Gaussian vectors landing in the same coset modulo the lattice, then the result will in fact be a Gaussian vector. And this immediately suggests an algorithm. The algorithm starts out the same as the AKS algorithm, except now instead of looking at, so I start out with many, many vectors. Now I really care that these vectors come from a discrete Gaussian distribution. That's like very important to me. But I don't look at all vectors simultaneously. I restrict to their cosets. So these vectors are all in the same coset, which means that their averages are all lattice vectors, which hopefully you can see. So all these purple vectors are their averages. So what the algorithm does, it looks at one coset, it pairs up all the vectors, it takes their averages to get some purple vectors, then it looks at the next coset, does the same thing. Then it looks at another coset, etc. Here's the full algorithm. This is the fastest known algorithm to solve SVP. You start out with many vectors, sample from the discrete Gaussian, you pair vectors according to their coset, you take averages of their pairs, and you repeat. And finally, of course, you output the shortest non-zero vector that you see. What we were able to prove is that modulo some caveats, the vectors stay Gaussian at every step if you do this. And this algorithm runs in 2 to the n time. And it runs in 2 to the n time because there are 2 to the n cosets, and I have to iterate through each coset, right? There's one coset for every parity vector. So that's the whole algorithm. Let me just summarize. The situation right now is that we have a 2 to the n time algorithm for SVP. We have a 2 to the n over 2 time algorithm for a slight variant of SVP that's good enough for applications. And of course, there's a ton of work that I'm happy to talk about offline that I've not discussed. In particular, there are other lattice problems. There are variants of SVP. I spend a lot of time thinking about short vectors. And I guess I'll just say that this 2 to the n over 2 algorithm uses the same idea. It just somehow avoids grouping vectors only in the same coset. It's a little more friendly about who it's willing to group together. A little less picky, I guess I should say. Okay, so now let me very briefly tell you about the sort of other side of my work where I provide evidence of security. And just sort of to get your expectations right, let me remind you that we don't know how to unconditionally prove security of any cryptographic scheme. That would be much, much stronger than proving that P doesn't equal NP, and we don't know how to do that. So I'm not going to give you a proof that this stuff is secure or anything close to that. And if I'm discussing the security of lattice-based crypto, I should say at the outset, the strongest piece of evidence that we have probably is that nobody's broken lattice-based crypto, even though many smart people like my advisor have tried. If I were talking about RSA or some other crypto scheme, I would have to stop here. Usually this is the only kind of evidence that we expect to have. But for lattice-based crypto, we have a little bit more. In particular, we know via reductions, we can prove via reductions that breaking lattice-based crypto is at least as hard as breaking, as solving some other computational problems that we think are hard. We prove that formally via reduction, right? We show that if A is hard, then B is hard. So I've already shown you one reduction that's kind of trivial. If you can break lattice-based crypto, then you can break SVP. That's not very interesting. Sorry, if you can solve SVP, then you can break lattice-based crypto. That's not very interesting. I also described to you another reduction. We have this NP hardness result, which shows that you can reduce an NP hard problem to SVP, which proves that SVP can't be solved in polynomial time, assuming that P doesn't equal NP. What we also have that I mentioned sort of briefly to David is worst case to average case reductions, which prove that some variant of SVP, an approximate version of SVP, is no harder than breaking lattice-based crypto. So if you can break lattice-based crypto, then you can find short vectors. And if you can find short vectors, then you can break lattice crypto. So if you squint, then breaking lattice crypto is equivalent to finding short vectors. But of course, this word approximate here is hiding a tremendous amount. So let me not say too much more about average case hardness, but what this tells you is that if P doesn't equal NP, then there's no polynomial time algorithm for SVP, and there's probably no polynomial time attacks on lattice crypto. But I'm worried about a 2 to the square root n time algorithm, right? So instead of using sort of the standard reductions that we all know and love, I use what are known as fine-grained reductions, which are actually kind of a trend in computer science right now. Instead of saying A reduces to B, so if A is hard, then B is hard, I say A with input size exactly n reduces to B with input size exactly 2n, which means that if A is 2 to the n hard, then B is 2 to the n hard. And I can use this tool to prove much stronger than just polynomial time lower bounds. I can prove very concrete lower bounds. So with Devesh, Huck, and Sasha, we use this rough idea to show this 2 to the epsilon n time algorithm, lower bound that I described before. And this is assuming a widely believed conjecture called gap ETH, which is the assumption that you can approximate 3-sat in better than exponential time. In particular, we know that there's no 2 to the square root n time algorithm. And we also know stronger hardness results for closely related problems, assuming different assumptions like SCTH. For example, we have nearly tight lower bounds for the closest vector problem, which is a closely related problem to the shortest vector problem. And if you're willing to change the norm, if you're willing to change your definition of what counts as short, then we know very strong lower bounds for SVP as well. So I'm essentially done. Let me just sort of briefly tell you what I hope to do in the future. So the sort of holy grail for me would be to prove that one particular crypto scheme, I guess I have a specific one in mind, but anyone would do, is secure. So it can't be broken in time better than 2 to the 128, let's say. That would be amazing. But this is like a, this is the holy grail. This is a pipe dream. I don't plan on doing that. I don't claim to expect to. That would be much, much stronger than proving P doesn't equal NP, if not formally, then at least morally. But what we can do is we can prove hardness of problems closer and closer to crypto. This is kind of related to Carlos's question. Like SVP actually provides us a really natural way to do that, which is just to prove hardness for approximate SVP for larger and larger approximation factors. So lattice-based crypto is a very natural approach to this. Oops, wrong direction. I'm also, oops, sorry. I just want to close this problem, right? So we have a lower bound of 2 to the epsilon n on SVP. We have an upper bound of 2 to the n over 2, or 2 to the n, depending on who's counting. And I want to just know the right answer. Before a few years ago, I wouldn't talk about this in public, but now I think we will. I think I'm going to finish this problem, or we are going to finish this problem. We're going to have tight upper and lower bounds on this problem, and then we won't have to think about it anymore, which I'm very excited about. There are lots of other things I want to do in this direction. For example, I want to improve worst case to average case reductions beyond the best that's currently known. I'd love to prove that we can get crypto from the hardness of some complexity class. There's been a lot of recent progress on that. And I'd like to show that lattice crypto is at least as hard as other crypto. Say, if you can break lattice crypto, then you can factor. That would be really quite comforting to me. Anyway, I think I'm about on time or over time, so I'll stop there. Thank you very much.
Thank you, Noah. That was a great summary. And I guess I assume you're happy to answer some questions if people are interested. You can either raise your hand or speak up. And while you're not doing that, maybe I'll start you off with a question. I'm a little worried that I asked you this question at your actual interview, but nonetheless, I'm going to ask it again.
I'll forgive you.
If I didn't ask. So one thing I love about lattice-based cryptography is this average case to worst case reduction.
Yeah.
That is the fact that even if it were the case that factoring in the worst case was hard, who the hell cares? That's not what I was using. It's using random numbers.
Exactly.
But lattice has the reduction. So what's the strongest actual statement, conditional or otherwise, that you know on average case lattice hard, something that's hard on the lattice side, but it's an average case hard? Like what's a concrete statement that we know is hard on the average case on the lattice side?
The concrete statement, leaving out the parameters, is that if you can break lattice-based crypto, which essentially amounts to solving SVP in the average case, or some version of SVP in the average case, then you can find short vectors in any lattice in the worst case. The rub is what we mean by short. Right, so there are two ways in which we change the definition there. We don't even consider the shortest vector, we only consider the shortest basis. We allow for a rather large approximation factor. The approximation factor itself is n to the 1.5, but that is probably completely meaningless to you. It's not even obvious whether polynomial or exponential or constant is what's reasonable. It turns out to be n to the 1.5. But I should mention that, like, in a lot of ways, the reduction is really good. For example, the reduction preserves the dimension, which is like really kind of impressive, I think. So there really is kind of a sense in which an average case lattice is the worst case lattice. The gap is entirely in the definition of shortness. Did that answer your question?
Yeah, it does. Thank you. Other people have questions or want to suggest?
Yeah, I had one or two. That's all right. Thanks for a very nice talk, Noah. I have what is probably a dumb question, but I'll ask it anyway. Is it clear that it's easy to test whether a given vector is a shortest vector in a lattice? No. In other words, is it in NP, known to be an NP or not?
It's not an NP to confirm that a vector is the shortest, right? But it is. But like the formal NP problem would be like find a vector of length at most this, right?
No, I
Or
want to.
I
I
guess
want to
like, if you
ask.
wanna-
Is it? Yeah. Okay. So. Okay. Right. So I would like to ask: is how hard is it to decide whether a given vector is the shortest vector in the
yeah,
lattice?
I guess that's co-NP complete, right? Because determining whether a short vector exists is NP complete. So determining whether no shorter vector exists is co-NP complete. Does that make
Right.
sense?
Okay. Yeah. 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 Okay.
Yeah. It is known that if you're willing to give up an approximation factor, again, these are probably meaningless to you, but an approximation factor of square root n, then the problem ends up being in co-NP. So in other words, then there does exist a witness.
Okay. Why would you think that would be meaningless to me?
Oh, the factor square root n? Because I feel like out of context, like
Yeah. I
the
see.
difference
Okay.
between square root n to the 107. Or
Okay.
It's a polynomial in n. It's a not
yeah, but
insanely.
even knowing why
Okay.
polynomial in n is reasonable, I have no idea.
Right.
I always
It's a
feel
not
weird
an
talking about
insanely big polynomial in n.
I
Yes.
have another question too. In your sieving algorithm, is there is there any idea of how the points distribute among the cosets, or is that pretty uniform? Are they pretty uniformly distributed?
Good. So originally we made sure that the distribution was exactly Gaussian, which was not exactly the algorithm I showed you. That requires a little pre-processing. You do some rejection sampling. Now we discovered that you don't need to do that. And if you don't do that, then we get some super wonky distribution over the cosets. It's a really nice question. It turns out that we don't care what the distribution is. We kind of know what it is, and it's hideous, but somehow we don't care.
Okay.
This is
Good.
very intriguing, especially the word hideous. What way is it hideous?
Well, it has a closed form expression, but the closed form is well, it depends on what you consider a closed form, but it's like this weird summation over all the cosets, this weird thing. A lot of things about this algorithm seem tremendously natural. That's one of the things that seems completely unnatural and seems to come out of left field.
And then one final thing, maybe a solution to one of your open problems. You said you would like to find a relationship between some complexity class. And I'm wondering if you have considered the possibility of defining a complexity class based on lattice-based cryptography, and then your problem would be solved.
Yeah, it seems a little like cheating, right?
Well, no,
I mean,
not if there's a lot of, if there are a lot of things that you can do with that. You know,
that's
maybe you
true.
can show,
I mean,
yeah.
so what I was more thinking about, so there's the sort of like Papa Dimitriou group of TFMP classes.
Yeah, or the, yeah, or
And
the
there's been some recent
original,
progress showing PPP completeness of problems that are very closely related to lattice-based crypto,
yeah.
which is really quite exciting. There's also some work on, sorry, I'm blanking a little, on PPAD, proving some versions of PPAD hardness for problems that are very closely related to lattice crypto. You're right, I could just define the class, but it would only be interesting if I could show that lots of things were in the class. And right now I don't really know of anything that's in the class.
Right, okay. Well, thanks a lot. I have to skip out. I have a 4:30. See you later on.
Thanks, Dexter.
So if there are more people, more questions, I'm sure Noah is patient enough to answer. I don't see other hands up. If there are no public questions, then I guess the custom is that we go over to GatherTown, whose URL I just put in the window. And I hope many of you come over to GatherTown and get a more private option to ask questions from Noah. And meanwhile, you can maybe unmute your mic and clap your hands so he feels like there's a little bit of reward for giving a talk. So thank you, Noah.